Hi everyone, so welcome to lecture 3, and in today's lecture we'll actually cover binary classification, and in particular we'll cover the simplest binary classification, in some sense the oldest binary classification algorithm called the perceptron algorithm, right? And very interestingly, actually perceptron has its seeds in a lot of the modern machine learning classification algorithms, in particular deep neural networks, also called multi-layer perceptron, right? So the simple perceptron, also called the single layer perceptron, which was introduced quite some time back, kind of has its foundations in a lot of machine learning that is done even today, right? So that's why I think it's important from a historical perspective to actually know and understand a lot of these kind of foundational machine learning classification and regression algorithms, right? So today we'll focus on classification, in particular the perceptron. Okay, so this is part one, and in part one we'll actually kind of do a recap very quickly of supervised learning, but more from a perspective now of classification, right? So if you recall, in lecture one we saw the basics of machine learning. We looked at different kinds of machine learning, right? Classification, regression, ranking, recommendation systems, etc., etc. Right? We also looked at the ways we can deal with basically varying amount of data, right? So we have supervised learning, and so on, right? So within supervised learning now, in lecture two, we looked at regression, right? And we kind of did a deep dive on regression. So today we will take a look at classification, right? So I'll do a recap of supervised learning from a classification perspective. Then I'll talk about the notion of linear separation and what it means to basically separate between different classes, right? And with that, then we'll be able to set up the basics of the perceptron. Okay, so interestingly, it turns out that the perceptron has a very interesting kind of history. I'd actually encourage you, if you have some time, to actually just kind of look up the history of perceptron. So actually it turns out the perceptron was introduced in 1958 by this paper by Frank Rosenblatt. In fact, there are a few papers that kind of talk about similar things, maybe before even the 40s. But Rosenblatt actually was, one of the first to come up with the name of perceptron, right? And the way he introduced this was actually more like a general purpose machine that can actually classify all kinds of things, right? And actually at that time, Rosenblatt was very, very bullish about perceptron, and in some sense, to some extent, you can see that his claims were a bit too much, if you will. So that kind of caused a little bit of a controversy in the 1960s. There was some New York Times article and so on and so forth. But it turns out that very quickly other researchers started kind of studying this and understanding more of the limitations of perceptron, right? So soon the limitations of perceptron became evident. For example, as we shall see today, it works only on linearly separable cases, right? And in fact, Marvin Minsky, who's also kind of known as the father of AI, right? He basically kind of published a paper trying to understand perceptron a little bit more, and he basically, for example, showed, I think this was somewhere in the maybe end of 1960s or early 1970s, he showed that perceptron cannot learn a simple XOR function, right? So it means that perceptron again is limited to some extent because of the linear separability, right? But I think one thing to keep in mind is that in some sense the seeds of the multi-layer perceptron were planted in perceptron, right? And a lot of future research like support vector machines, for example, which came up in the 1990s to early 2000s, again is kind of built on top of perceptrons and has kind of a similar flavor, just the loss function is slightly different. Though the way you view support vector machines, actually we'll see this in the next class when we introduce support vector machines, is different. But it turns out that the loss function is a kind of a variant of the kind of perceptron loss function. In fact, a lot of deep neural networks are built in this way, but by stacking perceptrons, stacking layers of perceptrons. So they're called multi-layer perceptrons. Okay. So yeah, so with this, right, I'll briefly kind of again recap. We have seen this actually in the first lecture. We saw this also in the second lecture. So I'll go over this now very quickly. This is the setting. I'm just going over this again and again because I think this is really important for folks to understand, right? So I think it's important to understand how the kind of paradigm of machine learning, basically the kind of foundational aspect is to get the training data, right? So this is basically M training data points, right? And then the kind of goal, again, I'll just kind of emphasize this again because this is super critical, right? So the goal is to actually learn this function f, right? So that f of xn is a good approximation of my ym, right? And I want this good approximation on unseen x value. So I want to generalize. Right? These are the three main takeaways over here, that I have my training data first. I want to learn a good approximation of my labels, right? And I want to do this on unseen data. I think these are the three most important pieces to understand from a supervised learning perspective, right? So today we'll actually study classification. Okay, so we also saw this last time. So there's a training data, and then we saw last time in lecture 2, we actually went over regression, right? So in this lecture and actually a few coming lectures, we'll actually focus on classification, right? And in particular today, we will look at the binary classification case. So this lecture will be focused on binary classification, but in the following lectures, we'll actually introduce basically multi-class classification, how to address multi-class classification using binary classification algorithms. Okay, so again, a recap of the hypothesis space, that these are all the allowable functions f that my model assumes that my model can take, right? And in fact, a lot of these in these lectures, for example, today's lecture as well, and even the previous lecture in lecture 2, we looked at the class of linear functions, right? So for a long time now, we shall actually focus on linear functions for some time. But soon we'll actually get into non-linear functions and how do we model linear, non-linear functions, right? So given this class of functions, basically, then the goal is to find the best elements in this hypothesis space, right? And this often is a searching or an optimization problem. So for example, in lecture 2, we went over gradient descent based algorithm to actually do the learning problem, right? To solve the model parameters. So this is an optimization problem. And the way you can do optimization is using gradient descent, for example. This is one of the techniques, right? And finally, then once we do this, we want to see how to measure the quality of F. So this one is evaluation, right? So with this now, again, kind of the main 5 steps of machine learning, right? So the first is to collect training data, right? And then select the model F and the loss function L, right? The reason why I'm again and again kind of bringing this up is because even today's lecture, even perceptron, we'll see, right? Essentially, perceptron, you have a certain kind of model F, a certain loss function, and a certain optimization problem, right? So in some sense, you can abstract all of these different machine learning algorithms into choices of a model, a loss function, and an optimization problem, or an optimization algorithm, right? Once you have these 3, you exactly get a machine learning algorithm, right? And finally, in some sense, this is a training step, right? These 3 are training, and these 2 are evaluation or test, right? So in test or evaluation, you obtain the predictions on the test data and then you evaluate. Okay, so you have a certain error function that measures the evaluation. So again, as I emphasized, I'll again emphasize that we will see that actually perceptron has a specific model class, right? So there is, it turns out it's again the class of linear functions, right? So we'll be looking at the model F belonging to the class of linear functions, and then there is a perceptron loss. So we study the perceptron loss, and then we will actually solve the learning problem using a flavor of gradient descent. So this is slightly different from linear regression. Again, in linear regression, it is the same thing, right? So linear regression also had F as being linear, right? Then L was the squared error, right? Or the N2 squared loss, right? And finally, the entire problem was solved using gradient descent, right? So it was convex as we saw, and then we could solve it well using gradient descent. So here also we'll see this is still convex, right? So we'll be able to solve it using a flavor of gradient descent. Not exactly the same as gradient descent, so we'll see this actually in the second part of this lecture. Okay, so again, the supervised learning workflow. So you collect training data, you select the hypothesis class, so select F, right? And then you select L over here, right? So choose a loss function, and then there's the optimization, oftentimes gradient descent, right? And finally, we'll actually evaluate the quality, right? So this is actually evaluation slash test. Okay, all right. So now coming to binary classification, right? So I think now we kind of have the requisite kind of knowledge again. So, sorry, I just wanted to spend some time to just make sure to recap of some of these things. So we have binary classification, xm is in Rn, these are my features, and ym is +1 or -1, right? So these are my labels, and I just have k equal to 2 over here, so I just have 2 labels. So this is binary classification. Okay, so you can think of the observations point in Rn with an associated sign, right? So you have the +1s over here and the -1s over here. So I want to build a classifier that can essentially, so I want to build a classifier, right? That basically is something like f, such that after I get f, I want to be able to say that if it's greater than equal to 0, this is positives, and if fx is less than equal to 0, this is negatives. Okay, so in some sense, what I want to do is I want to be able to form a separation f of x, right, and say that this space is f of x greater than 0, so this is my positive space, and this space is f of x less than equal to 0, so this is my negative space, right? Of course, as you can see, in this particular case, it's not kind of separated it completely, right? So the question is that if I have data like this, what's a good hypothesis space, right? Well, it turns out in this case it's actually non-linear, right? So that means that if I want to truly separate it, I will need to come up with a kind of somewhat of a contrived decision space, something like this, right? So this is somewhat of a contrived decision space where this is my f of x. It looks highly complex and highly non-linear, right? So this is the space of fx less than 0, fx greater than 0, right? But keep in mind one thing, keep in mind one important thing, that I just don't want to memorize my data, right? So the goal is not to come up with this. So basically this f may be very complex, right? But I don't know, for example, that some of these points, right? So I'll just highlight some points. Maybe some of these positives could actually be noisy positives, right? So they could actually be negatives, but they are labeled wrong, for example, right? Similarly, maybe some of these negatives, right, may actually be positives, which are labeled wrong, right? So again, I don't want to make my decision space too complex, right? So this is a very complex decision space. I don't want to make my decision space too complex, but indeed, if my data looks like this, then this would be kind of the more complicated decision boundary that I want to learn, right? So this boundary, for example, is a very non-linear decision boundary, right? So this is a non-linear hypothesis space. This may or may not be, the kind of right space, and the way to evaluate it, as I said, is to actually test it on test data, right? So I independently get a lot of test data, and then I can verify if this is if this hypothesis space is good or not, right? Another example of a hypothesis space is actually this problem, and this is much easier, right? So here I have probably a more simple function like this. This is my f of x, and then again I have this region as f of x being greater than 0, this region is f of x being less than 0, right? So this in all probability is going to be actually be a linear model, right? So I can write, that means I can find a fx which is basically A transpose x plus b, right? So I can find AB such that f of x parameterized by A and B, right, can separate this data, and by this data I mean this data, right? So this is the goal, right? And in today's lecture we'll be looking at one such binary classification algorithm called the perceptron, which is actually a linear classification algorithm. Okay. All right, so this is the same thing, right? So I have my linearly separable data, right? So the data, the observations or the data, right? The observations are said to be linearly separable if there exists a hyperplane or a straight line, right? In 2 dimensions, a straight line, where in n dimensions, a hyperplane, right? There exists a hyperplane which can separate between my positive classes, right? So these are my positive classes and my negative classes, right? So I have a hyperplane that can separate between these two, and then I can say that my data is linearly separable, right? So for example, this data as it is actually not linearly separable. So this is not linearly separable, right? Whereas this data is actually linearly separable. Okay, so what are linear separations, right? This is what we saw. This is a hyperplane. So in n dimensions, the hyperplane is a solution to this equation, W transpose x equal to 0, right? So this line that we see, that this line, right, this line, or over here in this case, this line, this would all correspond to a W and B, so that I have W transpose x equal to B, or plus B equal to 0, right? So what this means that this actually divides us into two spaces, right, where I have W transpose x plus B is greater than 0 and W transpose x plus B is less than 0. So this space are my positives and this space are my negatives, right? This is exactly what we saw over here, right? So we want to separate into these two pieces. This is fx greater than equal to 0, this is fx less than equal to 0, and this is the expression of fx equal to 0, right? So this is my separating hyperplane. Okay, so again, this is half space 1, which is W transpose x plus B greater than 0, and half space 2, W transpose x plus B less than 0, right? So this is so I'll just note this down. This is half space 1 and this is half space 2. Okay, cool. So I'll skip this and come to this. So this is data which is linearly separable, right? So I have basically my positives here and my negatives here. Again, this data is linearly separable. So I have my positives here and negatives here. So it means that there exists a hyperplane here which can separate between these two, right? Unfortunately, this data is not linearly separable, right? And the reason is that this particular example is kind of sitting right in the middle of my positive instances, right? So these are my positive instances. So if in case I do find a separating hyperplane like this, sorry, this is supposed to be a straight line actually, right? So even if I can find something like this, I would misclassify this example, right? So that means that this data as it is not linearly separable. Of course, I might still be fine with just using a linear classifier, right? I might be fine to say that, okay, I want a simple model. And very well, right? Very well, this example might actually be noise even, right? It's possible that some of these may be noisily labeled. That's also something to keep in mind actually. Of course, it's a little bit of an advanced topic, but it's important to have robust machine learning where you want your machine learning algorithms to be robust to noise because come on, face it, right? If you're having millions of examples being labeled by humans, there will be certain examples which are noisily labeled, right? So I don't want to over conform to things which are like noisily labeled. Okay, so this is maybe another case which is probably more realistic, right, where my data is actually something like this. So here my hyperplane, so the data is separable. Okay, so this data is not even separable. So I think this is something to keep in mind, that here the data, of course, I mean, you could have an arbitrarily complex kind of decision boundary like this, which, you know, does separate it, right? But you could also have data which is not separable at all, right? So no decision boundary can separate it. But on the other hand, there are data that are separable, right? So this data is actually separable, but not by a linear model. But in fact, if I have maybe a quadratic function like this, right? So a quadratic function that I've drawn over here actually can probably separate between my data, right? So again, these are my positives, these are my negatives, and this is my f of x, right? So I still have the same thing. I still have that this region right? And this region, right? So my green region corresponds to say fx greater than 0, right? And my cyan region, right, corresponds to fx less than 0, right? But just that over here f is say quadratic and not linear. Okay, so that's the difference, kind of the main takeaway over here, that we could have separable data, right? Or we could have data that is not linearly separable. I mean, not separable at all, right? And within separable data, there could be data that is linearly separable, that can be separated by a linear function, and data that would require more complicated functions to classify, right? So I think it's also important to distinguish between these two cases, right? So case 1 over here and case 2 over here. So case 2 is that the data is realistically kind of like this, right? Because you have so many samples that are kind of in this weird shape. That means that my features are not really linearly related to each other, right? So I really need a more complicated model. I really need a quadratic model to solve this, right? Whereas I have in case 1, it could just be the case that this red example is actually noisily labeled, right? So I might be fine to not really invest time to get a very complicated model. I might be fine just to use a linear model. Okay. Cool. So this is again the kind of recap of the same thing. So in my linear model, my f of x, right, is actually sine of w transpose x plus b. Okay. So this is the final classification model. So here in this notation, I was actually using f of x to represent the hyperplane, right? But another way you can actually write this is to say that f of x is actually sine of my my decision boundary, right? So that means that if w transpose x plus b is greater than 0, right, then f of x equal to sine of w transpose x plus b is actually plus 1, right? And similarly, if w transpose x plus b is less than 0, then f of x, which is again the sine of w transpose x plus b, is actually minus 1, right? So then in this case, if I have my data like this, I have my positives like this, and I have my negatives like this, right? Then this, all of this data would basically be classified as f of x equal to plus 1, right, and f of x equal to minus 1, right? So in this case, if you recall, right, the goal is to learn a f which is a good approximation of my y, right? My y's over here are actually plus 1, right? So this is y equal to plus 1 and this is y equal to minus 1, right? So I'm learning a f which is a good approximation of my y's by defining it in this form as sine of w transpose x plus b. Of course, we will see this a little bit later today, that I could also have a quadratic model, right? So I could define my f of x to be sine of, ax square plus bx plus c. So this is similar to the polynomial regression that we saw, right? So this is like a quadratic model. And in this case, if I have my data something like this, right, and my negatives are all over here, and then I have this, basically this decision boundary, right? So I'm able to separate my positives in this way, and I'm able to separate my negatives like this, right? So this would be an example of kind of a quadratic scenario. Okay. All right. So very quickly now, given this f, now that we have come up with the f, the question is what is the loss function, right? So we'll set up the loss function as well very quickly, right? So my hypothesis space is fx equal to sine of w transpose x plus b, right? So then I have a 0, 1 loss. This is my true loss, right? So this also is called the error, right? Which is equal to 1 minus accuracy, something like this, right? Which is kind of the inverse of accuracy. So my error, the number of misclassifications, which is called a 0, 1 loss, is just the sum of the absolute difference between ym minus sine of w transpose x plus b. Right? So if you recall, this guy can take either numbers +1 or -1, right? Similarly, ym can be +1 or -1. So if both yms and sine are of the same sign, right? So both are say +1, both are -1, then this difference is 0, right? But in the case when one is +1 and the other is -1, so they have been misclassified, right? The difference is actually 2. That's why you have a half over here, right? So half into 2 is 1, right? So this literally counts the number of misclassifications. Okay, so that's why this is called count of the number of misclassifications. The only problem though, this is a great loss by the way, right? And ideally this is exactly the loss that we care about. So why not just optimize this? The only problem is that this is actually tough to optimize, right? Because the gradient is kind of hard to compute for the 0, 1 loss, right? So it's actually not differentiable. And it's not even continuous, right? So the reason is that if okay, so suppose I were to plot over here, right? If I were to plot over here kind of the error, right, versus y multiplied by sine of w transpose x plus b, right? So if I were to multiply this quantity, then this guy is the positive region, right? This guy, so actually sorry, I don't need the sign over here, sorry about that. I'll just write this as y multiplied by w transpose x plus b, right? So if the product of these two things are positive, that means both are of the same sign, then my error is actually 0, right? But if they are of different signs, then my error is actually 1. Right, so you see over here, this part is actually, this is a part of this part is not continuous. Right, so because it's not continuous, it's actually hard to optimize this loss. Right, so in fact, before coming to this is exactly what this plot says. Right, so this is my loss function L over here, and this is my y multiplied by f of x. Right, so we see over here, this region is actually +1, right, when the y multiplied by f of x is less than 0, right, and it's 0 over here. So this part is a non-continuity, right? So as you can imagine, obviously we need to relax this, right? We need some kind of a simple way to relax, and that is where the perceptron loss comes in. Right? So the perceptron loss is the first classification loss we'll be seeing in this class, right? So it's somewhat important, right? And this was the kind of second part. So the first part is choose f, which we already saw, right? This is the class of linear functions. The second is choose L. Right? So this is what L is, the perceptron loss, and we saw that we can't optimize the 0, 1 loss, right? So we are looking at a relaxation of the 0, 1 loss. The relaxation is exactly this quantity. So instead of looking at the absolute difference between ym and sine of w transpose x plus b, as soon as I have a sine of w transpose x plus b, that is what causes the non-continuity, right? So how do I get rid of the sign? Well, what I can do is I can take a max between these two quantities, right? So suppose this quantity is negative, right? Then minus of that becomes positive, and the max of 0 and a positive number is that positive number, right? So what it means is that as soon as ym multiplied by f of x m, right, is the product of this is actually less than 0, right? So as soon as the product of this is less than 0, then I have this large loss, right? So my loss now is not necessarily anymore +1 or -1, but my loss is actually the product of ym multiplied by w transpose xm plus b. On the other hand, if this quantity is actually positive, right? So that means both y and w transpose x plus b are of the same sign. Then if I multiply a -1 to this, then the quantity becomes negative, right? And a max of 0 and a negative quantity is 0. So this is exactly what is kind of portrayed over here. So this region is where the w into w, the y multiplied by w transpose x plus b, which is f of x, is actually greater than equal to 0, right? So that region, my perceptron loss is 0, right? So perceptron loss is 0. But in this region, when y multiplied by w transpose x plus b is actually less than equal to 0, right? In this region, my perceptron loss actually is a positive number, and this is the plot of the perceptron. So it actually increases more my misclassification is, right? So in this region is actually larger than 1, for example, right? After this point, it is actually larger than 1, but over here is actually less than 1, right? So in some sense, you can see that this is kind of a relaxation of the 0, 1 loss, right? And this loss has a nice property because it is actually continuous, right? So I can actually optimize this in a gradient based formulation. And in the second part, we'll actually study how to optimize this in more detail, right? So to summarize the perceptron loss, the goal is to actually optimize the perceptron loss using gradient descent like formulation, right? But the perceptron loss isn't differentiable, though it is continuous, right? It is continuous, but it's not differentiable. So unlike the case of the squared loss, which was actually differentiable, right? So we could do the proper gradient descent. We can't do the standard gradient descent anymore because, well, the gradient may not exist for a few points, right? So we need actually a generalization of what it means to be a gradient descent of a differentiable function, actually. So I'll just replace this. So it's still convex, right? So it's actually a typo. This should be actually be differentiable, right? So it's still convex. The perceptron loss also is convex, by the way, right? The only difference is that it's not differentiable. So we need a generalization of a gradient, and that is exactly what we'll see in the second part of this class, which is what is a generalization of a gradient.